Hello, everyone, and welcome to Online Lecture 8, Part 2. So in this part of the lecture, we're going to cover just slides. We're going to cover the rest of the slides here, and we're just going to focus on some different kinds of ANOVA situations. We're going to spend a little bit of time on factorial ANOVA, but we're not going to go through how to calculate it or anything like that. I just want to show you some of the basic conceptual ideas about it, and then we'll talk very briefly about some other kinds of ANOVAs. Okay, so here is factorial ANOVA on the right side of this table, and the real take-home message here is the number of IVs, number of independent variables, or as they're called in ANOVA, factors. Okay, and you can see that this is the only test we have covered to date where there are two or more IVs or factors. Now, this suddenly makes things a little more interesting. Now, as opposed to just studying whether plants will have be related to depressive symptomatology in nursing home residents, we can look at plants along with gender. Okay, that might be interesting. Maybe plants work better for one gender more than others. Okay, so we can look at those things, and so that's probably more in line with something that you might be considering for your dissertation, because I think that most topics probably want you to adjust for or include another independent variable that's important. So the other thing that you can see is different is just that we have to have two or more groups of participants per IV. Now that, if you think about that, that actually makes sense, because we couldn't just have, if you had only one gender, let's say, for example, we're only going to include people identifying as male in this study, then it's really not an IV anymore. It's not an independent variable. It's a fixed constant because it's only males. So, of course, we need two or more groups for each independent variable. Okay. So let's talk about this a little bit. The cool thing about factorial designs is that you can test more complicated hypotheses, like we just talked about with gender and with plants. Okay. Two or more independent variables are studied to determine their separate and joint effects on the dependent variable. And what's kind of cool is you can include only between participants variables, like I just talked about with the gender and the different groups receiving the plants. Only within participants variables. Okay, that might be if we actually had three different kinds of plants, but each person would have a shot with each plant. And then the other variable might be another condition that could be the same. We could look at their meals, what kind of breakfast they have. So we could then kind of vary. So each person has either no breakfast or a healthy breakfast, and we vary that along with the plant type. So if we had, let's say, only two plant types, none versus bamboo, and we had only two breakfast types, none versus a full breakfast, full healthy breakfast, we already have the participants going through four different conditions, right? Because they have to go through, if it was only within, they have to go through no breakfast with no plant, and no breakfast with the bamboo, and breakfast with the no plant, and breakfast with the bamboo. So that you can see why when you get to within participants variables, why you can get all of a sudden it can really blow up your study, and it can really put a lot of burden on your participants to have to go through these different conditions. Okay. Nonetheless, you can look at using this technique. If you actually are lucky enough to have within participants variables, you can look at those using factorial ANOVA. And you can have both between and within participants variables, such as a mixed design. So this time we might consider having one variable, gender, which will be between, and then the other variable, the plant, where they you know, the different genders get a shot with each kind of plant. Okay. So let's talk about interactions, because that's the real power of factorial ANOVA. It's when sometimes a variable isn't enough to capture what's going on. Sometimes the role of one variable may differ depending on the value of another variable. That's an interaction. Okay. So back to our plant and gender situation, and this time we'll go back to two between subjects variables. So you either get no plant or you get bamboo, and you are either male, female, or in a third category. We'll just say a third category. We'll leave it there. And the interaction might be that for males, the bamboo plant doesn't make a difference. No difference at all. But for females, it makes some difference. And for the third gender category, it makes a huge difference. So if I asked you, okay, so what's the impact of gender on depression? You'd have to say, well, it depends on the plant. And if I asked you, well, what's the impact of the plant on depression? You'd have to say, well, it depends on gender. Now we'll go through another example to make this more clear, but that's basically the idea. If you can't answer a question like, how is your IV impacting the DV? If you can't answer that in a straightforward way, if it says, well, it depends, you've got an interaction. Okay. So let's look at this example with caffeine consumption and sleep deprivation. So in this setup, we're going to have different people in each of these cells, okay? So it's between subjects. So we have people who are not deprived and people who are deprived of sleep. Within those groups, we're going to have people with low caffeine consumption, medium caffeine consumption, and high caffeine consumption. So you can see we have 6 groups. So we can pretend for the moment that we have 60 people and 10 people in each of these cells. Okay. All right. So what we have now are some main effects and some interaction effects, at least some potential ones. The main effect is the influence of each independent variable on the dependent variable. And there's one main effect for each independent variable in a study. So looking back, we have a main effect for sleep deprivation. We'll see if there is a significant main effect. And we're looking for a significant main effect for caffeine consumption. Okay. Now, interaction effect is the joint or interactive effect of 2 or more independent variables on the DV, just like we talked about, when the effect of one independent variable depends on another. Now, in interaction, you'll see when we do these line graphs, and we had, you know, you saw one line graph when we were doing the repeated measures. Well, we're going to do one line for sleep deprivation this time. And so one line will be not sleep deprived and one line will be sleep deprived. And then we'll look at the different effects for the different levels of caffeine. And if those 2 lines are not parallel, if they will cross, even if they don't cross on the page, if they're going to cross at some point, you have an interaction. Okay. So let's take a closer look at this example. These numbers in the gray squares are your means. Okay, these numbers in the gray squares are your means. And by the way, factorial design comes with its own host of assumptions and whether you can use this test or not. And we're not going to get into all of that right here, but just so you know, they're out there. Okay. All right. So here are our low, medium, high caffeine consumption and our not deprived and deprived groups. So if we look across the means for not deprived, on average, we get a mean of 5.4. And if we look for an average of means for deprived, we'll get an average of 4.4. And by the way, this is their performance in a driving simulator. So how well they perform, how many correct maneuvers they make is what we're measuring. Okay, so that's our DV, how many correct maneuvers in the driving simulator. So it looks like not deprived is making more, we don't know if significantly more, but more correct maneuvers than the deprived group. That's not too surprising. And then caffeine, low caffeine, 2.2, medium caffeine, 7.3, and high caffeine, 5.3. So just looking across the caffeine levels, it seems like medium's the way to go. And it seems like being not deprived is the way to go. Okay, because not deprived gives you more correct maneuvers and medium caffeine gives you the more correct maneuvers. But is there more to this story? Is it all just about these main effects or is there an interaction? Let's look. Aha, we see some non-parallel lines for sure. These are crossing. And this interaction effect means that there is, this crossing lines means that there's an interaction effect between sleep deprivation and caffeine consumption. So let's look at it. So the dashed line means deprived. So, and the straight line, the non-dashed line means not deprived. So just as we had kind of seen in the previous example, if you're not deprived of sleep, then medium caffeine is the way to go in terms of making correct maneuvers in the driving simulator. However, if you are deprived of sleep, get as much caffeine as possible. However, even if you do get as much caffeine as possible, you're still not going to perform nearly as well as if you had been not sleep deprived with a medium amount of caffeine. So does sleep deprivation make a difference? Well, it depends on the amount of caffeine. Does caffeine make a difference? Well, which caffeine's the best? Well, it depends on your sleep deprivation. Okay. So let's talk a little bit about notation, because this is something that you will either encounter or probably have encountered actually in the literature, and this is factorial design notation. So here we have a 2x2 design. What does that mean? Well, the number of numbers is the number of independent variables. I see 2 numbers, 2 independent variables. Now, each number indicates the number of levels for each IV. So in this case, IV1 had 2 levels and IV2 had 2 levels. Let's go through this 2x3 design. There's 2 numbers. So again, there's 2 independent variables. But this one, IV1 has 2 levels and IV2 has 3 levels. This matches up with what we were just discussing with sleep deprivation and caffeine consumption, because sleep deprivation had 2 levels, caffeine consumption had 3 levels. Okay. So let's talk a little bit about the strengths and weaknesses of factorial designs. Well, the strengths, more than one IV allows for more precise hypotheses. You can actually control an extraneous variable by including it as an independent variable and the ability to find interactive effects. Okay, so I feel like we've talked about number 1 and 3, but what do we mean by number 2, control of extraneous variables by including it as an IV? Basically, if you are worried that, let's say I really am interested in sleep deprivation, but I know that caffeine can have an impact on how well we make maneuvers in a driving simulator. And I'm afraid that's going to impact my results. Just include it as an IV. Now I no longer need to be afraid. I'm controlling for that effect. Okay. Now, having said that, what's the weakness? Well, using more than 2 IVs, using more than 2 independent variables may be quite cumbersome. So you already saw that suddenly by including, if I just wanted to study sleep deprivation, I could have put 10 people in one group, 10 people in another group. That's 20 people. By including caffeine, I suddenly needed 60 people to have 10 per group. Okay. And then higher order interactions, when there are more than 2 IVs, are difficult to interpret. So if you can imagine, 2 independent variables is kind of complicated. 3 is even more complicated. And my old stat professor used to say that 4 independent variables was proof of a higher power. For a 4-way interaction is proof of a higher power. And of course, I mean that as a point of humor. But anyhow, the point being that higher order interactions are just more complicated. So I would never, 3 is okay if you really have to, but I wouldn't encourage it. And I definitely don't encourage anything higher than 3. It's just something to keep in mind as you're planning out your dissertations. Okay. So now, as promised, we're into the last section here where I'm just going to go through and talk about some different kinds of ANOVAs and compare them. So the one-way ANOVA, if you remember, has 1 continuous response variable or 1 continuous dependent variable, in this case, test scores, compared by 3 or more levels of a factor variable, in this case, level of education. So we have college degree, graduate degree, and high school, and we see the various test scores for the 3 groups. And I don't know why they ordered it in this way. I guess they ordered it alphabetically, college, graduate, and high school, but I probably would have ordered it slightly differently. I probably would have ordered it by level of education, because it just would have made for a more interesting graph. But it's fine either way. Two-way ANOVA example. Okay, so this is like our factorial ANOVA. Okay, that's what we're talking about here. We have 1 continuous response variable, test score yet again. And now we're comparing it by more than 1 factor variable. So we have level of education and zodiac sign. And for convenience, we're only going to compare Libras and Pisces. So wow, the Pisces seem to do a lot better than the Libras across the board. And the more education you have seems to yield higher test scores across the board. Is there an interaction here? I don't know. We'd have to actually draft that out, right? And how would we do that? Well, I'd probably go ahead and make 1 line for, we're going to have 3 lines. No, we can have 2 lines in this one, excuse me. 1 line for Libra with high school. You can almost draw it off the edges of the bars. High school, college, and graduate. And 1 line from high school, college, graduate. Now, I think these lines actually, while they look relatively parallel, I think they're not completely parallel and would cross at some point. So you might have an interaction, but as with everything, is it significant, right? Is this interaction? We test it just like we test everything else. doesn't have a P that's less than our alpha, you know, P less than 0.05 or P less than 0.01, whatever our alpha is. Okay. Now let's talk about ANCOVA. Okay. So in an ANCOVA, we're going to compare a continuous response variable, test scores, by levels of a factor, like education, controlling for a covariate, number of hours spent studying. So you might be asking yourself, well, how is this really different from the two-way ANOVA we just looked at? The main difference, honestly, has to do with how you think about your covariate and that the fact that the covariate is continuous here. Notice the zodiac sign, Pisces, Libra, that was a categorical variable, right? You're either Pisces or you're Libra. Here, this covariate is a continuous variable, number of hours spent studying. Okay. Okay, now let's look at a one-way MANOVA. Okay, so MANOVA compares two or more continuous response variables, test score and annual income, by actually by one or more factor variables. In this case, we just have, oh, this is a one-way MANOVA, excuse me. So it's by just a single factor variable, level of education. So for the first time, we're seeing two dependent variables. That's important. MANOVA stands for multivariate analysis of variance. And I should have said ANCOVA stands for analysis of covariance. I think that's what it stands for. Yeah. So in either case, now we're up to multivariate analysis of variance. Multivariate typically means more than one dependent variable. Okay. I think this might be the only test we talk about in this course, and it's really, frankly, one of the very few tests that can cover a multiple dependent variable situation. And even if you're in the situation, there may be reasons not to run the MANOVA. So we won't get into all those details now, but it's an interesting piece here. But if you're interested in how the dependent variables work together and how level of education impacts these jointly, the test score and the annual income, then a MANOVA might very well be for you. Okay. Two-way MANOVA example. Now we've got our level of education factor. Level of education factor with high school, college degree, and graduate degree levels. Our zodiac sign factor with Pisces and Libra levels. So the two-way MANOVA compares two or more continuous response variables, continuous DVs, test score and annual income, by two or more factor variables. So now, once again, because we're in two-way land, we can have interactions. Okay. And finally, a MANCOVA example. Now we have level of education, controlling for or including as a covariate this continuous variable of number of hours spent studying, and our two DVs, our test score and annual income. Okay. So as you can see with these, I obviously am not spending a ton of time. I just want you to have a sense for the differences between them and when you might use each one. Okay, all right. That is all I have for you guys. I look forward to seeing you on Wednesday and discussing this material further. Have a good one.